Okay, now we talk about cyclodextrin CDs here. This is not new to you as we have discussed early on in this lecture. So what are they? They are your cyclic oligosaccharide molecules here, built of a D plus glucopyranose unit divided, bonded via alpha 1,4 linkages. So other names include the Schrodinger, dextrins, cycloglucopyranose, cycloamylose, or cycloglucan. Now these CDs are only slightly soluble in water because you see the big molecule here, and it consists mainly of a carbon, hydrocarbon with oxygens, right? But their cavities are non-polar, so the more polar side are facing outwards here. The inward facing part is really non-polar here. So what do you think of the interaction between your substrate with the inner part of CD here? Think a bit more. Now, of course, you have got three main kinds of your CD, your alpha, beta, gamma, and they're pretty much just the numbering, the 5, 7, 8 glycopyranose units here. So pyran, how many carbon you have right in the system there. So these dimensions, again, don't memorize, but just know that the larger the number, the larger the diameter, okay, as the ring size increase, and you need to modify accordingly depending on your substrate size. So CD, we use them because of the good selectivity between the host and gas chemistry about your organic, inorganic molecule to trap ions right into the cavity here, or trap other particles here. So they do have this capacity for very highly hydrophobic solute because, as we mentioned, the internal part is really hydrophobic, and we introduced this term called K prime here, a kind of a rate constant, right? When it's the ratio between the number of moles of your MC over that of the cyclodextrin here, right? And of course, you can always relate this towards your K, which is your coefficient, distribution coefficient, using the concentration here. So number of moles is equal to the product of concentration and volume. Okay, and the interaction depends on how good the hydrophobicity of both the analyte and your cyclodextrin is. So for instance, if you have both are very fatty and there's lack of any binding hydroxy group here, of course they will complex very readily, which means the association is very high. But more importantly, what matters is also the size here. So if you have a good interaction but the cavity is too big and your molecule is too small here, just slip away, right? So the host gas chemistry binding isn't as strong here. So here again, we give you a table for the alpha, beta, gamma. Okay, your 5, 7, 8. Okay, so here we have this electrophoregram of using CD, right? We have a enantiomeric separations here. Okay, so these are all your MAT enantiomer here, right? But because the CD is there's a handiness inside here, it's chiral, so it's able to separate them. Okay, using a beta CD. Now, of course, we can have MEKC with your CD, right? So this is a diagram I think you have seen before here, where you kind of a host gas chemistry here, right? Your CD will bind with this solute here, right? After its detachment from the micelle. So you have this equilibrium, you have that equilibrium, you have another equilibrium, and last equilibrium. So there's many kind of a physical chemistry going on here. Okay. So crown ether. Crown ether are this cyclic molecule, quite a macrocyclic polyether because you have a lot of COC bond, and they're able to form kind of complex, where with organic and inorganic ions, because the lone pair on the oxygens here, they're able to have a pi donation, okay, to form this bond here. So we also see a complex formation based on the ion dipole interaction in this host gas chemistry, more of the inorganic chemistry at a high level. And it's really about the ion is totally charged, right? So it's an electrostatic attraction, and the oxygen has a delta minus, so there's a dipole, so ion dipole interaction. So typically, you have this kind of system of your crown ether here. You have 14 crown 4, 15 crown 5, 18 crown 6, 21 crown 7, 24 crown 8 here. And these numbers are not random, okay? So when you draw it out, then you can see that, okay, it's very symmetrical, okay? And you can see, so in this case, right, you see 18 crown 6. Why is it 18? Why is it 18? Think a bit more, okay? So you see this joint here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 6 oxygen in the ring, right? 18 points. Okay. So you see this in the middle, you have this ammonium ion, right? N plus, and then you interact with a dipole, ion-dipole interaction. This slide shows a formula to calculate the effective electrophoretic mobility difference between the two enantiomers, right? So there's a possibility of having two enantiomers being separated through chiroelectrokinetic chromatography by changing the average mobility. So the way to do it is, right, we have to also use the right CD. Now here in this case, right, you see that we have a substrate called the chlorine 9-amine. In the presence of this 2 mg per milliliter Cm beta CD here, what happens is, in a different pressure, you see that the resolution differs. So if we have this counterbalancing pressure, it will actually decrease the average mobility and overall increase the resolution of the separation between your enantiomers. Here's a schematic diagram of what happens. In A here, there is actually no counterbalance flow. In part B, there is a counterbalance flow, and therefore, when you have this delta P here, it will change the difference in the migration speed of the enantiomer A and B much more. And overall for C, the resulting mobility of A and B will differ. So if you have achieved C, in which these two comes in opposite side, then the RS, the resolution, will be large. And in this formula, you can tell that, right, and if the mu average is very small, then the resolution becomes very large. Here in this case, right, what we can do is, when we change a parameter, for instance, in this, we are changing the pH here, with the same mixture of the enantiomer here, what happens is one of the enantiomer gets eluted first. So here you see the migration time. On the left-hand side, right, the negative enantiomer migrated faster, right? But if we raise the pH to still the acidic zone, but a bit higher, then the plus isomer comes up first. So there's also a way to reverse the enantiomeric migration order. Here in this case, we have another mixture. We have the enantiomeric isomer mixture of the chlorine 9-amine, and this is in the presence of 3.5 mg per ml Cm beta CD. Now here, for A, I would like to see that, right, in the absence of counter pressure here, the separation of the positive and negative enantiomer isn't that great here. But when you have low counter pressure, just slightly, but even with a bit of this counter pressure here, you see a stepwise change. So for the longest time, we have not seen an overlapping peak of the positive enantiomer over the negative here. Now this is a graph where we superimpose the two layers here. So there is no difference between the height of the negative enantiomer because you have the same amount in terms of concentration. So that's why the sorbent's height is the same. But what you see is, although the negative enantiomer comes up later, right, it only comes up first a bit less than 150 minutes compared to here about less than 25 minutes. But what you want to is to separate the enantiomer here. So of course, with a bit of counter pressure, we have achieved that. In this case, pay attention, you have this hydroxythalidomide, which is very dangerous. Now, here on left, right, you have this 5-hydroxythalidomide, because you have a chiral center here, so you have this enantiomer 1 and 2. And in this case, you have the 2 chiral centers here. We call it the trans 5-hydroxythalidomide. 3 and 4 peak comes out in a pair form, and 5 and 6 your cis 5-hydroxythalidomide here. It comes in a pair because we are trying to have this enantiomeric form. For the pure thalidomide, it comes out at 7 and 8. So in a carrier mode chiral EKC, this is a chiral selector not only responsible for the enantiomer selectivity of the separation system, but also for the transport of the analyte to the detector. So the sub-advantage associated to this mode is that the analyte migrates to the detector only when they are associated with the chiral selector, which means that, right, when they participate in the recognition process of the CD with this enantiomeric analyte, then you see a difference in the separation. Here you see the example of when you introduce more than one cyclodextrin. So what happens is, right, here you see First of all, we have this TM beta CD, right? But if you add a secondary cyclodextrin with the same affinity, what happens is it will increase the separation factor, so the peak become even further compared to before when it's just a solid tube on its own without any addition cyclodextrin. However, if you add another form of cyclodextrin here, the HS beta CD here, what happens is it has the opposite affinity effect for this substrate. We have a warfarin, a thin blood thinning agent, WF. Then what happens is the resolution decreases because it enhances the overlap. It will bind more strongly to negative warfarin and therefore doesn't allow it to separate. So the key idea from this slide is that it's not saying you can add any cyclodextrin. It will always increase the resolution. You have to add the right kind and amount of a CD here, and to do so you have to test it out and do experiment like this. Then you can see, okay, if I add another secondary combine your Caro selector, then you have a better resolution. So as a summary here, we talk about the different kinds of buffer with different pH working range, and also different micelles, how it affects neutral compounds, other kinds of modification to enhance the selectivity, and also the resolutions, in the CE here. Okay, of course, we talk about the microemulsions, polymer ion pairing exchange, different kinds of association, dissociation constant, having the kind of CD, cyclodextrins, crown eater, right, the gas and host chemistry, and of course, aptamers in the last lecture, and now the chiral separating agent.